Okay. Good morning, everyone. I'm really pleased to be part of this meeting. ACME will do great things. And this morning, I want to share with you a global overview on massive black hole binaries. And just note that this is work that includes some of the work that we are doing in France in a collaboration between IAP, IRAP, APC, and the Observatoire de Paris, led by many early career researchers. So this is probably not particularly important for this audience, but when we look at gravitational waves in the same way that we think of telescopes looking at different wavelengths, you need different gravitational wave observatories to detect gravitational waves at different frequencies. And with the frequency for merging compact binaries, scaling inversely proportional to the black hole mass, for massive black holes with masses larger than 10 to the 4 solar masses, we need to have low frequency detectors, in particular LISA and pulsar timing arrays, looking at millihertz and nanohertz respectively. Something that is very important when we think of gravitational waves and electromagnetic detections at the same time is really the power of constraining the evolution of massive black holes in a way that is not possible with gravitational waves or electromagnetic detections alone. This figure is taken from the proposal to ESA that led to the adoption, to the selection and then the adoption of LISA. Here you see different massive black holes evolving over time from their birth at early cosmic times and high redshifts with relatively low black hole masses from a few hundred to this massive one, more than 10 to the 5 solar masses. And these black holes then grow over time, accreting gas. These are these smooth mass increases or merging with other black holes. These are the dots that also show a jump in black hole mass. And when they merge, so every time we have a dot, they emit gravitational waves. And so if they are in the band of one of our detectors, we will detect them. And you can see here the reach of LISA, for instance, detecting the large majority of the evolution of black holes. When they accrete, we see them with our telescopes. And when they are in this region, then we can see them at the same time through gravitational waves and electromagnetic radiation. Eventually, when black holes grow enough, they become sufficiently massive to be detected with pulsar timing arrays. So LISA is really going to constrain and characterize the early growth of black holes. And for a large majority of the time, there will be a possibility for a joint detection. Pulsar timing arrays have revolutionized our understanding of low frequency gravitational waves with a detection in 2023 hinting that if what is observed is fully comprised of massive black hole binaries, there is a large population of merging black holes. Though there is a possibility as well that part of the signal is in individual sources that are detectable above the noise. So let me guide you quickly over 13 billion years of evolution of how massive black holes and galaxies evolve and the various questions and physical approaches that we are trying to use to understand them. Let's start with the very beginning, black hole formation. Contrary to stellar mass black holes that inhabit this region with low black hole masses, for the very massive black holes, we don't really know how they formed. There are several mechanisms proposed. They can cover a different range in black hole masses with very often not well characterized initial mass function in terms of actual masses, but also number densities. There's expectation that the first stars leave behind massive black holes in the range of about 100 solar masses, and these should be numerous. At the other extreme, we have more rare systems forming supermassive stars with masses up to perhaps 1,000,000 solar masses, but these should be rare events. In the middle, we have also an analogy with what we see for stellar mass black holes and intermediate mass black holes, formation in dense star clusters. There is also the possibility shown here with these woods, being lost in the woods, lost in the forest. This is how Gillian described this, is what for us astrophysicists is a more exotic scenario, meaning that black holes may be forming just after inflation or around the time of electron-positron annihilation, and creating a population of still unknown and uncharacterized, even theoretically, of primordial black holes. Or could be anything else, or a combination of this. I think this slide is a cartoon, but really gives a very good feeling of the status we are in. We can try to make this a little more quantitative. In particular, here, the light blue and gray areas are anchored in observations. We have the stellar mass black holes, the end of lives of massive stars populating all galaxies in, up to 1 billion in the Milky Way or so. And the massive black holes that observationally are above 10^4 solar masses that are well characterized at the high mass end, but a bit less in the mass regime below 1,000,000 solar masses. So here, these different scenarios for black hole formation are highlighted with chunky boxes, again showing our ignorance. Now, this is a field that has picked up very much recently, in particular in light of JWST discoveries of a large population of AGN at high redshift. And in particular, what we are thinking nowadays is that instead of having separate boxes, we can think of these different black hole formation mechanisms as more like a continuum, where depending on the environmental conditions, we can have more or less massive black holes, star clusters, and even supermassive black holes, with the understanding that most likely we have this type of sequence in terms of masses and number densities. Now, we start with SIDS with masses between 100 and up to 1,000,000 solar masses, if we're very optimistic. But then what we observe is more massive black holes, 10 million, generally 10 million solar masses and above. And a key point that has been highlighted in the last couple of years, triggered by JWST observations, is how do black holes grow at high redshift? Historically, theoretical models used to predict a number density of active black holes that was much higher than observations. So in this plot, you see an estimate of the observed luminosity function of AGN, and different theoretical models shown here in orange, green, and blue. And in particular, here, these models differ by the effect of supernova feedback. Early models of supernova feedback were weaker. This is in particular because early simulations were lower resolution and we couldn't capture the explosion of supernovae, the evolution of the blast wave. But as we have more resolution and we can model better supernova feedback, we see that the effect of supernova is actually stronger, and in particular decreases the growth of black holes. We can see this in the luminosity function. So the blue curve, which has a more realistic supernova feedback, predicts a lower AGN luminosity function, and also shows that the black hole growth is suppressed in low mass galaxies, and only in large galaxies it picks up and creates a large population. So this was really the state of the art until 2023. We were happy that we had finally reduced the growth of black holes at high redshift that was nagging us so much with the luminosity functions. But then GWST came along, and all of a sudden they found luminosity functions that are much higher than observationally determined before. So this is shown in this plot. The pre-GWST observations were extrapolations of the observations per se reached about 10 to 12 solar luminosities, but their extrapolation is even in the most optimistic scenario, again, for observers, theorists were already predicting very large population of AGN, fall below the number densities now GWST suggests. So the question is, should black hole growth be more efficient or go back to the number densities that we were finding earlier on? Well, it's still a bit unclear. So here we have, well, the first point is that GWST is not detecting only very active, massive black holes at high redshift, but also very massive galaxies at high redshift. So it seems that overall there is a milder requirement for any type of feedback at high redshift. So a possibility that was suggested is that perhaps if these AGN are growing and accreting, they provide the energy to suppress star formation when needed instead of supernova feedback. So this is a very active field of research. But the other thing that I tend to say is that these GWST results are very recent. And so some of the analyses rely only on one indicator of AGN compared to what we're used to, that with multi-wavelength AGN characterization. So at the moment, this is really a field that is incurring many novelties, and it's finally something. The high redshift AGN is something that's not just theory, but has now become part of the observational field as well. Now, besides forming and growing black holes, when we care about gravitational waves, we also have to think about merging black holes. This is an incredibly hard task from the theoretical point of view, trying to model this. The reason is that if we want to understand and characterize and therefore interpret gravitational wave observations of merging massive black holes, we have really to model an impressive range of scales. So black holes merge when galaxies merge. But to understand how often galaxies merge, we have to go to a cosmological setup to understand really the merger rate of dark matter halos and galaxies. And large-scale structure is something that we need to model on scales of hundreds of megaparsecs at the very least. Then when two galaxies merge, we have the effect of gravity on about kiloparsec scales that brings the two galaxies together. And when we're lucky, the two black holes will also find each other at the center of galaxies. This is through a physical process called dynamical friction. And then when the black holes form a binary at about parsec scales, dynamical friction is not efficient anymore, so we have to rely on new different physics to bring black holes to coalescence via gravitational waves on milliparsec scales. So you see here that in principle, if we want to really understand this process, we have to cover scales from hundreds of megaparsecs to scales that are less than 1 milliparsec. How complex is that? Incredibly complex. So if we think of cosmological simulations that resolve the large-scale structure, the typical resolution is about a few hundreds of parsecs. We can have, some that are about 30, 40 parsecs, and most of them kiloparsec scales. If we think of this in the context of the evolution of black hole binaries, this misses really all the evolution from when the black holes find each other in a galaxy, meaning that all the juicy part is something that we have not really been able to understand self-consistently until very recently. So already now it's almost 10 years that we have at least started to resolve the dynamical friction phase, meaning what happens on about kiloparsec scales. We can analytically calculate the amount of force that should act on the black holes on smaller scales and add this force to the black holes and have them evolve naturally down to the resolution limit. This gave some surprises. When I was working on this like 25 years ago, it was very easy to model galaxies as spheres. We all love isothermal spheres. And the decay of an object, in this case, a black hole in an isothermal sphere, is beautifully just analytical solution. And so it's a deterministic event. But then we realized that, when we started running simulations, that high-redshift galaxies are really not isothermal spheres. You see here an image from a simulation by John Regan, in which you can really appreciate how messy, non-spherical symmetric the distribution of masses. This also means that the gravitational potential is very shallow. So when we drop black holes in this potential, or more than drop, when black holes form in this potential, they're really not going to evolve smoothly on circular orbits in an isothermal sphere as we're used to, but they more have like an erratic dynamics that leads them to evolve in kind of random fashion. This affects both the ability of black holes to grow by accreting gas, just because they move in and out of these dense, turbulent gas clouds, but also the ability of black holes to bind in binaries. It is much less likely than two black holes find each other if you're randomly moving in a potential, rather than if they're slowly falling towards the center of a deep potential well. Really, in the last few years, there have been at least two attempts to go beyond this phase of dynamical friction and really follow black hole evolution all the way to milliparsec scales. This has been done with two very different approaches. One is CATU, is a clever approach to add resolution very close to black holes are. And then it's similar to an n-body code, just much more efficient. So literally CATU follows all the phases of black hole evolution to coalescence, although only in systems that are not, that don't have much gas, meaning that the evolution in circumbinary disks cannot be captured by this type of integrators. The other approach, which is called RAMCall, is what we call a subgrid model, meaning that we integrate analytically the equation of motions and the accretion growth on black holes using the information that we have on the grid, in the same way that we model star formation, supernova feedback, black hole accretion, and black hole feedback. With this approach, we have included dynamical friction, the effect of feedback, interaction with scattering with stars that evolve the binary evolution, the binary serial major axis, evolution in a circumbinary disk, gravitational wave emission, agent feedback. And so now we're more able, I mean, it will never be a perfect representation of a realistic galaxy, but we're more able to cover this range of scales from hundreds of megaparsec to milliparsecs as the simulation runs, rather than in post-processing as we have been doing in the past 10 years or so. So this is, these developments have been both very recent. So we don't have large-scale simulations using these approaches yet, but it's really something that we hope to have in the near future. And I want to move towards multi-messenger science with massive black hole mergers. Touching on the various phases of their dynamical evolution. So thinking back of the evolution on kiloparsec scales, black holes are just separate black holes. Each of them can light up and act as an AGN, as in our normal single AGN. On smaller scales, when the black holes form a binary, then you expect to have binary AGN. Binary AGN would be really on sub-parsec scales when the two black holes are tightly bound. And finally, the phase of merger itself. What are the probabilities of finding electromagnetic counterparts and associated transients for, in particular, for LISA? Let me start with dual AGN. Dual AGN have been studied now for a long time. The first discovery was NGC 6240 in 2003. It was the discovery of two X-ray nuclei that showed that black holes actually do find themselves in the same galaxy. This has then, been supplemented by many explorations, finding now not only dual but also multiple AGN using different approaches from X-ray to optical to infrared to radio. But these are cases in which the black holes find themselves on kiloparsec separations in one galaxy, or they're hosted in different galaxies. So we can look for the same systems in cosmological simulations. These are some examples from a simulation called Horizon AGN, in which we have something similar to NGC 6240, two black holes, two AGN, actually, close by in a galaxy merger remnant, and also black holes in emerging galaxies and multiple systems. So here the cyan crosses show real dual AGN, meaning that they are at small separation, while the green plus signs, these are just chance superposition, suggesting that indeed in the same astronomical image, we could have both real and apparent multiple AGN in the same way that we look for galaxy pairs, but we have to be careful about systems that are very close in projection, but very far away in redshift distance. When we look at this dual AGN, something that I think is very important is to distinguish when we see dual AGN in one galaxy, like NGC 6240, or in separate galaxies. This means if we see two black holes in the same galaxy, it means that the black holes, that the galaxies have merged already, so that we are already in a late stage of the evolution. When we see black holes or AGN in separate galaxies, this is even before the galaxies merge. In other words, the dual AGN in separate galaxies may fool us much more often than dual AGN in the same galaxy in terms of being a bona fide binary and leading to a black hole merger. Indeed, if we look at the fraction of dual AGN in the simulation that eventually lead to black hole mergers, if we look at dual AGN in the same galaxy, the probability that the two AGN will eventually lead to a black hole binary is about 90%. And this drops to about 70% for AGN, dual AGN hosted in different galaxies. Now, the top panel is a very optimistic approach in which we assume that black holes merge very quickly after galaxy mergers. The bottom panels are a bit more pessimistic or realistic, depending on how you want to see it, in which we include in post-processing the time delays that we expect is dynamical friction, scattering of the binary with stars, circumbinary disk evolution, gravitational waves that lengthen the time scale of the black hole merger. And you see that the fraction of dual AGN that lead to a black hole merger now becomes smaller, but remains still high for dual AGN in the same galaxy, and in particular, if they are luminous. So here the dotted curve is for bright AGN with a luminosity larger than 10^44 ergs per second, compared to the solid curve that has a luminosity of 10^43 ergs per second. So dual AGN are a good signpost for black hole mergers, but most likely have to correct the merger rate that you get from dual AGN to obtain the actual black hole merger rate. Going closer in, looking at binaries at sub-parsec separation, this is also a very active field of research. And there will be many talks at this meeting, so I will not go into much detail. Just that in this configuration, when you have a circumbinary disk forming also small disk around the black holes, you can have various effects from periodicities in the light curve to changes in the spectral features, emission line profiles, presence of shocks, or kind of holes in the spectral energy distribution caused by empty regions in the disk. So Vincent will give his own talk. Just a quick advertisement that periodic binaries can be looked for and found in existing surveys already. I don't want to give more details because Vincent will talk about it. A question that is often asked is, are merging black holes found in merging galaxies? This depends a little bit on the types
Marta,
of systems. Yes.
so Marta, to interrupt you, you have 1 minute left for your talk.
Sorry, I couldn't hear you.
You have 1 minute left for
Perfect.
your talk. Thanks.
Okay, so let me skip this, just say no. And then let me go to the detection of electromagnetic counterparts for gravitational waves with LISA. So we take a full sample of simulated black holes. We model the AGN SCD and various transient phases. These are for high redshift black holes. LISA sky localization is not ideal. The large majority has poor sky localization. You can ask me more and I will give you details, meaning that most likely we have to tile the sky or focus on low redshift binaries. Oops. Interesting point is, what type of mergers do we detect electromagnetically and with gravitational waves at the same time? A basic requirement is that your black hole is active enough that you can see it over the noise, which is the galaxy. And for the large majority of high redshift sources, the X-ray flux of the AGN is comparable to the X-ray flux from the galaxy itself, X-ray binaries, meaning that when we look at the systems that we can actually detect, they will not be an unbiased tracer of the full population. Let me focus in particular on this plot on the right. So here blue is the relation between black hole mass and stellar mass for all merging black holes. And then the green and red show the cases where we can detect a merger. So we will be finding black holes that are overmassive at fixed stellar mass, something that is on top of other biases that we already have. So this leads me to my summary. Massive black hole binaries, and pretty much every item that I've discussed is very uncertain and an active area of research. From the theoretical point of view, we have made much progress, but we're still trying to understand many details. But I hope that I have shown you how rich the joint gravitational wave and electromagnetic exploration of massive black hole binaries is. Thank you.
Thank you very much, Marta. It was very, very nice talk. So we have time for a few questions.
Hi, thanks for the really nice talk. Naive question. So do we expect then all supermassive black holes in these systems to act as AGN?
You mean in binaries or?
Yeah, in binaries and, within the kiloparsec scale.
Oh, no, not at all. The lighting up of AGN is very stochastic. So you would see systems as dual AGN only for a fraction of the time. It's really, the amount of the inflow of gas depends on the region where the black holes travel in. So a significant fraction of the time you can see one AGN. You may also see none at any time. Regarding binaries in particular, there is a lot of debate, but probably Alessia can answer this, Alessia Franchini better than me, about the accretion on the last phases of the merger, considering that torques expand the gas in the silicon binary disk.
Okay, thank you.
Thank you. More question?
Ciao Marta, thank you for the great talk. I'm Michela. And thank you for summarizing the achievement of KTU versus Ramcol. Can you briefly walk us through what will be the main changes that we expect from including the binary black hole evolution and black hole evolution in general, real time instead of post-processing?
Well, lots of them. I cannot even start it. So, in terms of gravitational waves, the main point is that we will be able to follow the mass ratio evolution and the eccentricity over time. This is very important for waveforms, in particular if we have in this intermediate mass ratio regime that is very tricky to model, eccentricity as well. At the moment, we just assume circular orbits because we have no better assumption. And then in terms of time scales, at the moment, if you do it in post-processing, you either assume a circularity eccentricity and you just go with it analytically, or you can try to follow it through galaxy outputs, but they're usually separated by tens or hundreds of mega years. And so you end up with a very poor representation of the evolution. So I would say that pretty much everything needs to be revised.
Okay, thanks, Marta. We have time for one question more only. No? So maybe we can move to the next talk and we have time for discussion at the end of